Okay, so this is the last part of our lesson on circular motion until Tuesday. Um, and before we go into the next section, I'd like you to have a go at this task, which is to calculate the angular velocity of the minute hand on a clock. So I'd like you to pause the video here, look back at the formulas that we've used to see if you can find a solution. So for this problem, if we go to our definition of angular velocity, so omega equals delta theta, change in angle, change in time, and see if we can apply that. It's a good start with these sorts of questions, a good way to start. So if we're thinking about one path of the minute hand around the clock, our change in angle is going to be 2 pi. And the next question you've got to ask yourself is how long is it going to take for the minute hand to do that on the clock? And the answer is going to be an hour. So our delta t is going to be 1 hour, which we've got to convert into seconds. So our units are right. So we end up with 60 minutes in an hour and 60 seconds in a minute. So we end up with 3,600 seconds in an hour. So we do 2 pi divided by 3,600, and that gives us 1.74 times 10 to the minus 3 radians per second, and that's to 3 significant figures. You could have used pretty much any of the formula that we looked at in the last section to solve that problem. Obviously, it doesn't matter which one you use. I find it easier to remember sometimes just the one thing. So this is why I've gone back to this important definition, the rate of change of angle with time, to solve that particular problem. Now, what we're going to move on to look at is what is the connection, if any, we can find between the regular velocity and the angular velocity. We've already seen that we've got these important quantities, displacement, velocity, and acceleration for our linear motion, and for our circular motion, we've got these quantities. We've said we can forget about angular acceleration for our course because all the situations we're going to look at are going to be ones which have a constant angular velocity. So therefore their angular acceleration is going to be 0. So to see if we can get a link between velocity and angular velocity, we're going to follow a derivation. Now the skills that you're going to learn in this derivation are going to be very useful for you, for those of you going to go on and study engineering, physics or maths at university. You are not required to know how to do this in the exam, but for those of you pushing yourselves to higher grades with this, it is important you understand each step and why we're doing each step. And the result that we're going to get to is really important. So our question is, what is our link V and omega? And to do this, we are going to look at a circular orbit. Now this derivation will work with any circular orbit with a constant angular velocity, but just so we can picture it, let's go back to our example of the Earth, top-down view of the Earth orbiting around the Sun. And what I want us to imagine for this is we're starting here, we take a snapshot, and then an instant after, a very short period of time after, we take another snapshot. Now, I'm going to exaggerate it in this diagram, but if we think about what a snapshot in time is going to look like, the Earth is going to have moved slightly further along its orbit. So we've got the Earth now have moved to that point there. Now, what I'm going to say is the difference in time between those two positions is, I'm going to call it delta t. Now, I'm calling it delta t with the lowercase delta just to represent the fact that it's a very small difference in time between these 2 points. And in that point, or in that time, sorry, the Earth has moved through an angle of delta theta. Yet again, a little delta to show that it's moved through a very small change in angle. The Earth has gone from there to there in that small time. It's going to work for any orbit, any circular orbit, this. So I'm going to give the distance or the radius of that orbit there as being r, which is the same as it is up there. Now what I'm going to do is I'm going to expand on that diagram. So I'm going to go from looking at the whole thing just to this section. So if I do that, I'm going to end up with something that looks a bit like this. And this angle is going to be our delta theta, and it goes from being there to being there. And we know that this radius there is r. At this point, it's helpful to remind us of the definitions of the things we're trying to connect. So our angular velocity, our definition is the change in angle divided by the change in time. In this case, our change in angle is this small angle here, delta theta, and our change in time is our small time interval in which the snapshot's been taken. So we've got the fact that omega for our situation here is delta theta divided by delta t. For our regular velocity, we know that our definition is the rate of change of displacement with time, delta s over delta t. And in this specific situation, we've got v is equal to our delta s, I'm going to come to that in a second, and then divide that by delta t, which is our small change in time here. Now, this is the tricky part of this derivation, and it comes down to this delta s here. Now we know that this is part of a circular path, and if I was to ask you to show the displacement on this diagram here, it would be a tricky thing to think about because we've got this small angle. Now, what I want you to imagine here is that that angle is made small enough so that this curve of the circle here is effectively a straight line. And we can then, rather than thinking of the displacement as this weird curved line, for this small section, we can think of the displacement, delta s, as being given by this line, this straight line there. That is the reason why I've considered this as being a snapshot of very small time. And that's the only reason why I can do this derivation. Now, with this displacement delta S, I want you to think back to your maths and this idea of arc length. So arc length is going to be important in this topic, and it's given by the formula theta r. You may recall from maths that what's important here is this has got to be in radians for that formula to work. If theta's in degrees, that formula becomes more complicated. And that's partly why I said earlier that when we deal with angles and circular motion, we 99% of the time to deal with them in radians so that we can use this idea and use what we're going to derive from it. So this arc length is theta r. Well, what is our arc length in this case? It's going to represent our displacement delta s. So I can say delta s is going to be our theta. Our theta in this case is our little theta, delta theta, times by the radius r. And I can substitute that now into that formula to get v equals delta theta r divided by delta t. Looking at that in a little bit more detail and comparing it, looking at this, we wanted a connection between v and omega. Both of these equations have got delta t in it, so it makes sense to try and eliminate the delta t. So if we rearrange this, we get delta t v equals delta theta r, therefore delta t equals delta theta r over v. And then from this formula, we can see that delta t is equal to delta theta divided by omega. So we've now got two equations for delta t. Let's set them equal to each other. So we end up with, from this equation, delta theta over omega equals delta theta r over v. What's helpful at this stage now is we've got delta theta, both sides which cancel out, which then leaves us with 1 over omega equals r over v. If I then change that equation with a simple rearrangement, I get v equals r omega. And this is the key result that I wanted from this derivation. And it shows that there's a clear relationship between the regular velocity, our linear velocity, and our angular velocity. In fact, to get the linear velocity, all we've got to do is times the angular velocity by the radius of our circular path. For the rest of this lesson, I'm going to be setting some questions for you to do. It's really important that you put some time and thought into these, because next lesson, on Tuesday's lesson, we're going to be looking at the idea of centripetal force and also exploring this connection between the linear velocity v and its role in circular motion in more detail.